All right, hell yeah. So we're in this book, Mathematical Methods in the Physical Science by Mary L. Bowes. And I'm just going to make a quick video on rotation again because we're kind of getting better at kind of talking our way through it. Here is the two rotation equations. We're working with vectors, which is just a point in 2D space. And so I can be like, hey, that point is represented uh, x, y. I'm going to go over in the x and then up in the y. And so we're first going to start with this lowercase x, y input, and then we're going to rotate it up into that. And so the most important part about this video is that we need to look at convention. Convention for rotating a point, we're always going to be rotating that direction as a positive rotation, so counterclockwise. So if I start here, a positive rotation is going to be there. And then just in juxtaposition, if I actually say that we're going to rotate an axis, well, and it's not in juxtaposition. If I say I'm going to rotate this axis from this xy, 90 degrees, into a new xy frame, I'm going to rotate counterclockwise. And then the other take home, though, is that we can only ascribe the input of this equation as a vector point, and it can only output a point. You know what I mean? So those are the two things. It can input a point, it's going to change that location, and then it's going to output the new point. This one is going to say we rotated the axes, and it's like, but still, we're just inputting a point, and then we're outputting a point. The interesting thing about this is the output of this point is measured from the new axes. And so if the input point is xy, measured from this xy axis, the output is going to be the same point, but measured from this new x prime, y prime. And what happens is this point technically doesn't move, under, this, so it doesn't move, but we're just measuring it from the new location. But if you do look at that it does move, that's why I made a video of just like, if we start with this xy point, the lowercase xy, like, hey, and treat it like a piece of candy. This point is way farther away from maybe you. Let's say this x-axis is you, and this and this y-axis is your friend. You know what I mean? And then you're at 90 degrees or whatever. And then you're like, whoa, the candy's pretty far away from me. But then you guys are going to rotate. And so look, you are now right there, and you're like, whoa, the candy is closer to me. So that is my tip this week. And that's my example that I use to be like, oh, I can totally see that now. I am closer to the candy. Well, start in that same location where this is our XY point, the candy is far away, and just rotate this point towards you. And so if I got this candy right there, then it would have been the candy would have been just as close if I rotated the point this way. And if I rotated this point this way, is going to be a negative rotation. See how that's a clockwise rotation? Convention, we say that's a negative rotation. So I'm going to rotate this by a negative angle. So by measuring where this candy is from the new axes, if I'm saying the convention of rotating the axes is in this positive direction, it's the same as that candy just moving in a negative direction. And so that's what this first equation says. We're going to input a point, and then this is the matrix that transforms, or another word is it's the machine that takes that point and then moves it, to a new location. That's all it does in 2D space, moves it to a new location. Because the length doesn't change, it's just a pure rotation, but this is rotating by a positive theta. So the theta here is going to be a positive theta. Now this is kind of cool, especially the second part of this, is if I throw in a negative theta here, sometimes that's hard in an equation. Like let's say I had negative x, and then as that's my function. You know what I mean? So if I throw in the value of 0, I get 0. If I throw in the value of 1, I get -1. Throw in the value of 2, I get -2. So I have a function that's negative x. Sometimes that's very difficult to actually, a function is something that takes a number and then outputs only a singular number. And so, but I could have negative x, and I could, couldn't I just throw in a negative x? You know what I mean? So if I have a function that's negative x and I input a negative x, now I'm just back to a function that's very horribly explained, and that's the limit where it's just like, oh, is that like a change in variable? Seems like you just changed the variable. But yeah, so here for this, I can just input a negative theta. I want to know what happens when I do input a negative theta. You could just say, hey, I just want to input a negative 45 degrees, negative pi divided by 4. So if I do that, so sine of a negative number is just negative sine. And so then a negative sine of a negative number is a negative of a negative of that angle. When you have sine, these are percentages of the hypotenuse. So if you have a hypotenuse at an angle, the sine is going to be, and here's your angle. The sun shining rays are going to be on that vertical sine component, typically in the vertical direction if you're coming from the x-axis. It doesn't have to be vertical. But hell yeah, that's the sine component, the cosine component. Always percentages of the hypotenuse. So even I'm just catching myself. If I see sines and cosines, these are percentages of the hypotenuse. I just like to think, 0 to 100%. They can be negative, but just in a geometric, because if I'm below the x-axis, sine is going to be negative. And that's exactly actually what we have right here. The angle is going to be this way. That vertical sine component is going to be negative. So anyway, so we have negative sine of a negative angle is that component, and it's going to be a negative. So negative sine of a negative angle. The component is going to be negative, and then we're going to multiply by a negative, so that becomes positive. So it just becomes this, positive sine, negative sine. Cosine is kind of interesting because if I have a positive angle or a negative angle, the cosine is still, positive. So cosine of a negative angle is still the same as the cosine of that same positive angle. And so you could put two negatives here, but they'd be redundant. Negative cosine theta reduces to cosine theta. And so hell yeah. And again, I'm just trying to make this video just because I forgot to make a video last night. Okay, so we have, and I think there might be one more aspect to this. So let's talk about this. I'm going to input an XY point, and then it's going to say we're going to change our axes. But sure, the axes rotated or the point rotated in the opposite direction, because there's no difference. And I'm going to make a longer video, and my voice is getting destroyed. Excuse me. There's no difference in having this XY axes and then labeling this also XY. Sometimes I think that's useful because you're just like, well, I think it's easier to see that this is the XY, that you're measuring the point, and this could just be also an XY that you're measuring that location. So that's all we're doing here. We're taking this XY point, and then we're outputting it, and then just measuring that XY point. So that's, and it's really that's the mechanism that we're trying to do. And so we're having this lowercase xy point relative to these axes, but then we're just like, hey, I want to measure this same point, but relative to these axes. So that's what we're doing. And to do that, the only way to do that is actually to rotate this point in a negative direction. And so I think that catches me off guard, that if you're going to rotate axes, you're just rotating the point in a negative direction. Because if you rotate the axes in a positive direction, that point is getting closer to the x-axis. So it would be just like this point rotating in a negative direction. Hell yeah. And then kind of the final thing, and then we'll turn this video off, is just because you're going to get equations like these where, separated, this is C, this is our matrix transformation. And then we're going to input, for this, we're actually going to input the rotated position. So that's kind of interesting. If this is my vector r prime, I'm going to first describe it based on the x prime, y prime axes. So I'm going to be like, I'm going to go over here and then up there. And then when I do this transformation, and then so let's just kind of intuit our way through this one. After I do this transformation, I'm just going to measure this point from the x, y axes. Well, let's talk about it as a piece of candy. If I'm the x axis, and now I'm measuring this point, that point's hella farther away. It's like, oh shoot, the candy got farther away. And so I'm just even saying for myself, that means that candy rotated in a positive direction. And the only way to take an input point and describe it in a new location is by, a rotation. If we're pure rotation, is by a rotation. And so this has to be the positive rotation transformation or machine or matrix, and it is. The negative signs up there, the positive signs down there. The rotation of axes, these are switched, and so that's kind of interesting. And then basically, if you're just taking, you have this equation where the C is your machine. To get the C to the other side, you have to multiply both by the inverse. This is an orthogonal. The determinant's 1. Do the determinant. Cosine squared plus sine squared is 1. And it's what is it? It's orthonormal. And so the inverse is just the transpose. And so you're just flip-flopping that negative and positive. And so anytime that you have this x prime, y prime as your input, and you're measuring it. And so this is an axis rotation. You're just doing it opposite of what the book was saying. But actually they said this actually occurs more often. So that gets crazy, where you're just like, so if I do have an axis rotation, like my input, am I measuring the input from the rotated axes first and then rotating it back to the original axes? That I do not have an answer for. I'm just trying to say, like, hey, if I input this new rotated axes, and just based on how you describe this, so at any point, I can have a negative angle here, and this picture actually flip-flops, and I'm saying that it got rotated in the negative. But just for a proof, we're going to start with the axes at xy. We're going to positively rotate them in the counterclockwise direction, and I'm just explaining to you that you can only input the point, and the point can only move. And so that's like the point's moving closer to the x-axis. That's you. The candy's getting closer to you. And so that rotation, by convention, is a negative angle rotation. And so, hell yeah. So if we took the original change in, I don't even know what I just said, but hell yeah. Axes is rotating in positive. The machine or the matrix that describes that would be the point moving that direction. But then we have to look at this one, because we just said this is we're actually describing the point as the x prime, y prime. So that's our input. This side is our input. This is the machine that we're going to, and so the candy is close to me, this x prime. And then after this transformation, then we measure it from the x and y axes. The candy is farther away from me. So that would have meant a positive angle change, which is associated with just, just a positive point change. So yeah, that gets me, because if this is the axis rotation equation, it makes huge difference whether your input is the x prime, y prime, and whether or your input's the x, y. And so that's just kind of using your intuition, but still, you're inputting a point x prime, y prime from, and you're describing it from that axis. Sorry, I'm not holding the camera straight. You're describing it from that axis. You're putting a machine on it, a transformation matrix, and you're moving that point. But the output is just saying, hey, we're or just the way this equation is described. It says, hey, I have this point x prime, y prime. That's what this r vector r, column vector r is. And then this output is x, y. And so, and I guess just by definition is that this is saying that if I do have an x prime, y prime input, I would have to be measuring it from the x prime, y prime axes. So that actually kind of gets to me too, is just like, that is the notation. So I'll have to be cautious about that, because if I do use this notation for prime, that means that I'm measuring from the prime axes. So I guess I can buy that. So this is an XY point measuring from the prime axes. This output is the same point. And so that's part of this proof, is like, hey, this point didn't move. I just want the output to be the location of this point from the XY axes. And so then, therefore, is there a transformation that would actually do that? And so that's where we look, well, okay, if you actually did go up this x prime, y prime, the candy's closer to you, so that's going to be my input. But then you say you want to measure the candy from this axis to there, and then the candy is farther away from you. And so even just from that basics, like candy's close, candy's far, what would my transformation be? The transformation would be that point, that candy was here, and now it's getting to here, and I'm the x-axis. And so the machine or the matrix to describe that change in point, or that, would have to be a positive angle rotation. So even though so that's what this machine is. This matrix describes a positive angle change. And so I think that really helps my intuition when it comes to this change in axes business. Is like, look at an equation like these. Sure, measure this point from the prime axes. The output is a point measured from the xy. I think there's notation where potentially this could mean a few different things. But from this picture, that's what we're trying to say. We're trying to say that this point is going to be the same location. This point in the x prime, y prime is equal to the y prime, xy axes. I guess you could have an equation here where you could say 2r is equal to r prime. And so, you know what I mean? But this equation, as they showing in this picture, says that we're taking an input point and we're measuring it from the prime axes. And then the output is that same point that did not change location. That's r is equal to r prime. And we're measuring it from the x, y axes. Okay, hell yeah. And I think it's very useful for me just to even, kind of make videos like these where it's just like, I'm not 100% sure, but I do have a little nuggets that are going to help me. And just to talk your way through subjects, like turning them into languages. And I think what's crucial is that at first you don't give don't care that you're going to make mistakes. You're going to, like in this video, I potentially could have just said the total opposite stuff. I was talking to my buddy at the surf wave. I was just like, yeah, physics is crazy, because there's always like two different like guesses. Like you could either, the angle could rotate that in the positive direction, or it could rotate in the negative direction. And so there's all these like branches where you get like two choices and both seem intuitively the same. And I think what happens is those stack up. Like you're going to have a system of 4 things where you could have 2 choices here and 2 choices here, or they could be 2 choices here and 2 choices there. And that's interesting, because that gets me thinking about like the final, like the March Madness. We have the March Madness where you have to choose the winners of, you have 64 teams going into the first round, and it's 50-50 chances. So you're just like, well, how hard could that be to figure out 50-50 and just guess 50-50% of the time that you're going to guess all of them right? But then they go from 64 to 32 to 16 to 8 to 4 to 2 to 1, and it's just mathematically there's not enough time in the universe. I mean, yeah, it's an improbable. There's just absolutely no way. So even just a few 50-50 choices that you're unsure about just really add up when it comes to learning math and physics. And so I just wanted to end with that, to be like, oh, those are brutal. So why not? Who cares? Like, there's got to be like, I mean, there's the feel for the intuition, even if you're actually going to be saying completely wrong things. I think it is good to film yourself and to show your weaknesses. And then if you actually listen to your video, which I probably won't for this one, I apologize. But it actually is just like, actually, I don't know. Maybe I could come back in a month and be like, oh yeah, like obvious, like that's weird to hear yourself on video where like now you're smarter. You're just like, oh yeah, you were slow to the punch even to discuss that topic and wrong on some things. So that's kind of fascinating. All right, hell yeah. Thanks for joining me. This is Mathematical Methods in the Physical Science. This book is wild. You know what I mean? We're into vectors, linear algebra, but there's differential equations. We're going to be, just all the physics that I've never done. Lagrange multipliers, I've never done. I'm looking really forward to this differentiation section. I think that's almost the next section. Okay, hell yeah. Thanks for joining me. Booyah.